Hi, I'm Miranda Cosgrove, and this is Mission Unstoppable. Coming up, making cells levitate is all in a day's work for this genius.
What we do in magnetic levitation is we actually force these magnets to repel each other.
And who needs GPS when you have a sky full of stars?
It's so cool to think about following the stars on a journey.
Plus, discover animals who make their homes underground.
That's right, owls that live underground.
And sometimes math can be a piece of cake.
It's a great example of an abstract mathematical structure. Look what we've got here.
Get ready to meet the scientists, inventors, and heroes who help make our world a better place. The future is here. The mission, unstoppable. You don't have to be a cool mutant to make things levitate. You just have to be a cool immunologist, like our next guest. Although, if you're a mutant, don't be afraid to study medicine. The sciences can be a great career for anyone.
Superpowers. Who hasn't dreamed they had them? Superheroes are my favorite. So when I got the alert from Mission Unstoppable headquarters that Immunologist Dr. Danielle Twum seemed to harness the superpower of levitation, I had to put on my favorite cape and mask and rush to her her lab in Northern California to see for myself. Usually, you have to wait to meet superheroes because they're super busy. So while I wait, I practice my own levitation skills.
Big strawberry, levitation. Let's do this, come on.
Come on, levitate. Levitate. You know what? Feels a little heavy. Feels a little heavy. You know what? You don't start with the big strawberry. You start with the medium strawberry. Come on now. Levitate to the skies. Ooh, shall rise. No? Okay, that's fair.
Nabil, what are you doing?
Well, I know that you levitate stuff, and I thought I would dress up as a superhero and practice on these strawberries. That's how you do it, right?
No, dude. You need science. Lose the cape. Let's go get a lab coat.
So how does Danielle harness the power of levitation? The answer lies in this colorful blue machine called the LevICell, which she uses to sort immune cells. Once the cells are sorted, Danielle can study the effects of medicines on specific cells.
How did you get into levitating cells?
I unfortunately lost an uncle to brain cancer when I was a child. So I was always interested in trying to understand how to make that not happen again to someone else. And that led me into a journey with the immune system. And here I am, levitating cells.
Today, we'll be levitating Danielle's favorite immune cells, macrophages. Macrophages are cells in our bodies that gobble up all of the foreign cells that could cause us harm, like viruses or cancer cells. In order to understand how this is done, I need to know about two things: magnetic fields and density.
What do you know about magnets? I want to show you what magnetic field lines look like, because that's very critical to us being able to levitate the cells.
First, she explains magnetic fields. Danielle bore some iron filings over the magnets so we can see the force of the magnetic fields in action.
These lines right here are magnetic field lines.
Yes.
That's awesome.
Exactly, and it's in this pattern because these magnets are attracting each other, basically. What we do in magnetic levitation is we actually force these magnets to repel each other.
The magnetic field the LevICell creates forces the magnetic poles to push away from each other, making a field that looks like this. Then, they amplify the magnetic field by adding a paramagnetic fluid, which helps the magnetic field do its job. Danielle now does a demonstration to show me how density works. The ping pong balls with the holes represent dead cells, and the intact ping pong balls represent macrophages, the cells we're looking for today.
Already, I'm seeing the colored balls rise to the surface, and our dead cells are at the bottom.
If you put a dead cell in our system, it actually starts to take up the paramagnetic fluid, and so it causes it to sink. And the live cells, because their membrane is intact, they levitate higher.
Now it's time to sort real cells. We put the sample in the LevICell along with the paramagnetic fluid. The healthy, and therefore less dense macrophage cells should be pushed highest by the magnetic field, levitating them away from the dead cells.
Boom. So now you have the macrophages coming in into the system. And the reason why you have the green and the red is because we put some dyes on there to help us differentiate between a live and a dead cell.
So the green ones are the live ones?
Where are they positioned?
On top.
And the red ones?
Are the dead ones. On the bottom, just like the ping pong balls with the holes in them.
Exactly, and now we're collecting them?
Whoa! So that's us collecting them while they split into their respective tubes.
Separating these immune cells so effectively allows Danielle to run tests on them to see how they can help fight diseases like cancer. A scientist who uses magnetic force to help save lives? She really is a superhero in my book. I think I might need a better cape.
In my dressing room between takes, I like to check in with our experts. So I asked Danielle what she's been up to since we last filmed. Check it out.
Hey, Mission Unstoppable! Since filming with Nabil, a lot of things have happened. I left my lab work to focus on some bigger picture issues facing cancer patients. Understanding where patients are struggling is what will help researchers improve existing therapies and inspire new immunotherapies. I love being able to interact with people face-to-face to make cancer therapies accessible and equitable to all. And I'm very happy to be able to peek behind the curtain of all the STEM that is happening in this field. I didn't know this was even a possibility for a career move, which just serves as a reminder to always keep your mind open and follow your heart. Thanks again for having me, and see you next time. Bye.
The stars in the sky are beautiful, but they need to stop coasting on their looks. Our ancestors put those stars to work. Astronomer Athena will tell us how.
Every day, thousands of ships travel the world's oceans, carrying food, electronics, people, even cats. Oh, look at that little sailor. Modern boats navigate with the help of GPS satellites, advanced gyroscopes, and radar. But what did they do before those technologies? They used the stars. I'm Athena, your friendly neighborhood astronomer, and today I'm going to tell us how our ancestors used astronomy to travel the world. As early as 1000 BCE, the Babylonians were keeping records and using math to predict the movement of astronomical bodies. In the 2nd century BCE, a guy named Hipparchus of Nicaea compiled the first stellar catalog with at least 850 stars and their positions in the sky. Some call Hipparchus the greatest astronomer in antiquity. He used advanced spherical trigonometry to create astronomical models to predict things like planetary movements and solar eclipses. He might also have created the first trigonometric table. I love astronomy, but I've never developed a new branch of mathematics to learn something better. I feel like I'm slacking. Trigonometry is useful for a lot more than just studying the planets. It's essential for understanding physics, engineering, and especially navigation. In the Islamic world, scholars built on translated texts from the ancient Greeks, like my boy Hipparchus, and invented new instruments, like the astronomical sextant, which measured star positions and the tilt of the Earth much more accurately than previously possible. Over in the Pacific Ocean, Polynesian wayfinders developed incredible navigational techniques that let them travel thousands of miles between islands. They found their way with sophisticated understanding of bird flight patterns, sea life, wave swells, currents, wind direction, and of course, the stars above. A major tool for the Polynesian sailors was a star compass. And the cool thing about the star compass is that it is in your mind. Yup, the star compass was a mental construct. Navigators would memorize where certain prominent stars rose out of the ocean on the horizon and where they went back in. They called these houses of the stars, which I think is so cute. Just a little home for your blazing ball of plasma. To navigate, they'd start heading toward a certain star, and then switch to their next one once the first had risen too high. Like a map, you could follow a specific sequence of stars to your destination, sometimes thousands of miles away. It's so cool to think about following the stars on a journey. That's kind of what astronomy is, right? chasing the stars as they guide us to a greater understanding of the universe and even ourselves. Whoa, deep. I'm so happy to be part of this astronomical tradition with such a long and exciting history. I'm Athena, and always remember, per aspera ad astra. Bye, guys.
Living on land is easy. I've been doing it for years. But some animals are brave enough to live underground. We're gonna learn more about them right now.
Most of the time when I think about underground life, I picture a tiny little insect making its way through the soil with a little hat and a little briefcase, even though that's not realistic. But what if I told you that adorable bugs aren't the only creatures living underground? Hi, I'm Esther. I think nature is awesome and I want to tell you all about it. So we're gonna learn about my 3 favorite animals that live underground on today's Nature Side Quest. Number 1, moles. Since it's dark below ground, instead of relying on their eyesight, they navigate through the soil by touch, using their incredibly sensitive snouts. The snout of the star-nosed mole is surrounded by 22 tentacles that make it 6 times more sensitive than the human hand. This snout is so powerful that it can identify food in less than 8 milliseconds. These little guys aren't just great at finding food either. They're also great at tunneling through the soil. The eastern mole can tunnel through soil as quickly as 15 feet per hour. But even with all of that activity, you might go your entire life without ever actually seeing a mole in person. Next up is a legendary creature that poses a fascinating question. How much wood could a woodchuck chuck if a woodchuck could in fact chuck wood? Woodchucks, aka groundhogs, aka whistle pigs, are closely related to squirrels. These herbivores love to eat and can put away over a pound of greens in one sitting. Their incessant gnawing helps them keep their front teeth from getting too long because they never, ever stop growing. I can't imagine what it would be like if my front teeth never stopped growing. Try not to think about it for too long. Seriously, just stop thinking about it. And finally, burrowing owls. That's right, owls that live underground. Burrowing owls are the only bird of prey that are known to nest entirely underground. And when they hunt, they seem to prefer to catch their prey by walking or running along the ground. Can you imagine a tiny bird running toward you like this, with these legs and these eyes? While some of these owls do actually dig out their own homes, most of the time, they take advantage of the vast network of underground burrows, tunnels, and nests created by other animals. But sometimes the owls are the ones getting kicked out. Burrowing owls rely on flat open land, which is also the same type of land that real estate developers like to build on. As a result, burrowing owls are threatened or endangered in many of the states they call home. That's why it's important to know what's going on beneath our feet. What we do above ground has an impact on the animals living below, and we want to make sure that all these cool creatures still have a place to call home. That's all for now. I'll see you on our next Nature Side Quest.
Math is fun, but you know what would make it even better? Cake, for real. Check it out.
If I told you that studying math was as easy as pie, would you believe me? Well, pure mathematics can be. Pure math is about studying one thing and seeing a pattern, and then asking, well, if that's a pattern, then where else can I find that pattern? And today, mathematics professor Dr. Eugenia Chang is going to help me learn more about pure mathematics by baking.
I really love understanding how things work. Like when little children keep asking why, but why, but why? I was like that and I never stopped asking why. Welcome to the kitchen, where baking and math join together to make delicious and logical treats.
I hear that you're a pure mathematician. What even is that?
Pure math is about spotting patterns and understanding how things work, often so that you can make things yourself. Let's start with pie. What makes a pie a pie?
I'd say it starts with a crust, and then some fruit filling, a second crust on top, and then you bake it.
But what about this? Is this a pie? It doesn't seem to have fruit in it.
No, it's a quiche, but I could see why I would call it a pie.
And what about this? Is this a pie?
Actually, chicken pot pie is one of my favorite kinds of pie.
So chicken is not a fruit.
But it still could be classified as a pie. So if we define pie as something with at least one crust and a filling, then we can make an endless number of pies. Apple pie, cherry pie, shepherd's pie, pizza pie. I guess math really is as easy as pie.
Let's move on to cakes, and we'll put abstraction to work. Have you heard of a Battenberg cake? It's a great example of an abstract mathematical structure, so I thought we could make some.
Ah, that sounds great. A Battenberg cake's distinctive 2x2 check pattern alternates pink and yellow. Wait. I promise this will tie back into pure math at the end. To make the cake batter, we mix butter, eggs, sugar, flour, and baking powder. Then we add pink food coloring to half of the batter. We pour the batter into a tin and add dividers to keep the colors separate. And after 30 minutes in the oven,
So now the key is the Battenberg pattern. We have two colors of cake, and we don't want the same color of cake to touch the same color of cake, because that would be terrible. So then the question is, what possible patterns are there?
so I think we can do it diagonally so that none of the pink is touching the pink.
Right.
We spread the jam onto 12x8 marzipan rectangles and all of our cake pieces. Then we roll it up, make a few finishing trims, and our beautiful Battenberg cakes are ready.
Look at that, it's a Battenberg cake and a mathematical structure.
From adding zeros and ones to rotational symmetry of rectangles to multiplying positive and negative numbers, the list of examples of the Battenberg principle goes on and on. Or should I say on and off and on and off?
For example, we can make a little grid of what happens if we multiply +1 and -1. Look what we've got here. It's the same as a Battenberg cake pattern.
Ah,
We're spotting the same pattern in different places, and once you start spotting them, you can see more and more of them. And then you can ask yourself things like, how about bigger Battenberg cakes? And that's exactly how mathematicians think. They don't stop with anything. You admire it, and then you go, wait, what if I do this? What if I do something else?
Eugenia loves showing that math can be a piece of cake. And I love that you can have your math and eat it too.
Welcome back. Before we go, we have one last thing.
There will be moments you'll be uncomfortable, but sometimes it's in the discomfort that you become innovative. However, you should not let anyone get away with making you feel less than, because you're not.
Many people change direction later on in their life, and that you don't have to know what you're going to do for your whole life when you start out.
That's it for this week's Mission Unstoppable. Next week, I'm trying to get a marine biologist to name a crab Miranda Cosgrove, but she's not responding to my texts. Bye! If you're watching this, you must have really liked the video. Make sure you follow and subscribe, and check out these other videos that are even better. No, really. I've seen this one over 100 times.